Hello students, welcome back once again. Today we are going to see some general methods for simulating random variables. In the last video, we have covered simulation of a uniform random variable, manual simulation, as well as a computer generated simulation. And we have used that for generating a permutation. If you have missed that video, please go and see that video. And now we will study something which are some general techniques for simulating continuous random variables. So here I am back with my presentation. We will discuss general techniques for simulating continuous random variables. So let us try to see what are the general techniques that you can have for simulating continuous random variables. Now here, if I want to simulate a continuous random variable, what I need to know is the CDF of that particular random variable. If I know the CDF, the question is, can I simulate a random variable? The answer is yes, but it is a partial answer because of some limitations that we will see when we will discuss this method. So the first method that we have is the inverse transformation method. It actually relies on some very famous principle, that is the uniform random variable. If you take x following distribution function CDF capital F, then what you can actually do is something like you can simulate a random variable having distribution x. So let us try to understand it in this fashion, that I have a random variable x which follows distribution f, and if I consider this is f is a CDF, and if I consider a random variable y which is equal to f of x. Now I will try to prove that this random variable is having distribution which is uniform over 0, 1. How can I prove that? Let us try to assume this, that I can prove this. So let us try to prove it. So in particular, if I consider if I want to compute the distribution of this particular random variable, that is probability of y less than or equal to small y. This is equivalent to computing probability of f of x less than or equal to small y, which is equivalent to saying that probability of x less than or equal to f inverse of y. To do this, I need f to be continuous. If f is discrete, this point is not uniquely defined. As you know from our quantile functions, that this quantile is not uniquely defined. Therefore, I need this. And if I can do this, then this is equal to f x of f inverse of y. What does this mean? This fx is actually f because my assumption is x follows f. Therefore, what I get here is f o f inverse of y, which is equal to y. Now, do I know a random variable which has this property? That property. So essentially, if I want to find the PDF of this random variable, I will call this as fy of y. Then I will just differentiate dy of fy of y, which is equal to 1, where because this y is fx, so this fx will have a range which is between 0 less than or equal to y less than or equal to 1. So dfyy is dy of fyy is equal to 1. That is, the density of this random variable y is equal to 1 from 0 less than y less than 1. Less than or equal to or less than, it doesn't matter, and 0 otherwise. So in this case, I have proved that the random variable is actually a uniform random variable. This proves my claim that any continuous random variable you give me, if it has a CDF f, then y is equal to fx will follow uniform random variable, and that brings us to our next method. That method is called inverse transformation method. So this is the inverse transform method. It relies on the theorem that I proved just now. So let us try to understand what is the procedure for this inverse transform method. I have a uniform random variable. I know how to simulate uniform random variable from previous class or the previous video. Once I have the uniform random variable, I can actually simulate any continuous distribution f and set x is equal to f inverse of u. This particular x will then have a random distribution which is given by the CDF f. I have already shown you the underlying idea. So let us formalize this idea into the proof. That is, first you start with f. If at all fx had some distribution, call it fx of a, which is probability of x less than or equal to a. Now this x can be any, this a can be any real number. This is by our definition, this is equal to f inverse of u, f inverse of u. So I will put this as probability of f inverse of u less than or equal to. Now, since I am computing this f inverse is computable, and therefore what I can say is I can switch f inverse to f in a particular way. Also remember that since I am computing this f, the CDF has a property that it is monotone, non-decreasing function. Right? F of minus infinity is 0, f of infinity is 1. So it is bounded between 0 and 1. It is monotone, non-decreasing. Right? So using that fact, I can always say that f inverse of u less than or equal to a if and only if u is less than or equal to f of a. This fact I have also used in the previous proof. And if this is the case, what is the probability of u less than or equal to fa? Because u is a uniform random variable, the probability of u less than or equal to fa is fa. Therefore, I have proved that x has a distribution f. So what is the takeaway from this particular theorem? The takeaway is you can actually simulate any continuous random variable if f inverse is computable. Let us now try to understand this example via one example. Sorry, let us try to understand this particular method via one example. So what is the example? Let us try to simulate an exponential random variable. We all know exponential random variable, let us say with rate function lambda or mean 1. Rate function lambda or mean 1 by lambda. In this particular case, we will consider that lambda to be equal to 1. So I have x following exponential 1 distribution. The CDF of that exponential distribution is given as f of x is equal to 1 minus e raised to minus x greater than or equal to 0, and 0 otherwise. So it's a non-negative random variable. It doesn't matter whether the random variable is negative or non-negative. Our method goes through. But in this case, it turns out that it is non-negative random variable. Naturally, I want to compute f inverse of this. So let us do it. U is equal to 1 minus e raised to minus x. This number is always between 0 and 1. So U is always between 0 and 1. Now, if I want to use the inverse transform technique, then I need to find the inverse of this f, which essentially reduces to, you put this 1 on the other side, or you put e raised to minus x on the other side and write e raised to minus x is equal to 1 minus u. The inverse of exponential is natural log. So that forces me to give x is equal to minus ln of 1 minus u. which is also equal to f inverse of. This is what our goal is. So now I know x is equal to f inverse of u. So now we will simply apply that this u is a uniform random variable. U follows uniform 0, 1. So minus ln of 1 minus u is equal to f inverse of u, and x will follow exponential 1. Now note that because I know how to simulate random variable u, which is uniform 0, 1, I was able to simulate an exponential random variable with rate 1 or mean 1. Okay. That u follows uniform 0, 1, then 1 minus u also follows uniform 0, 1. Why not use that to our advantage? For example, if u follows uniform 0, 1, distribution of u is same as distribution of 1 minus u. That essentially means that whether I write this 1 minus u or u, it's same. So I can write minus ln of u will follow exponential 1. Now can I generalize this for any exponential random variable with mean c? The answer is yes, I can generalize this, and this is the result. If x follows exponential 1, then cx will follow exponential c. This is known to you. So if I have a random variable which is minus ln of u that follows exponential 1, then minus c times ln of u will follow exponential c. And therefore I can simulate any exponential random variable just by simulating uniform random variables and taking a natural log transform. This is the example of exponential random variable, and this ends the demonstration of inverse transformation method. Now let us go ahead and see another method. In some cases where this inverse function is not properly computable, or there are some hiccups in computing inverse function. In those cases, we can rely on a method called rejection method. As the method suggests, it's a rejection method. So what it assumes is, we know some random variable, let us say y, which follows a density, which follows some distribution with density g, and I am able to simulate this by means of some method. Now my interest is in simulating the random variable x, which has density small f. How will I simulate a random variable x using my knowledge about the simulation of random variable y? This is a powerful method, and we will see its power in due course. So let us try to see what algorithm this method uses. So the algorithm is very simple. I will have a random variable y. I know how to simulate a random variable y. So I will simulate the random variable y using the density function g. Then I know how to simulate uniform random numbers. So I will simulate a uniform random number u. And now what I will do is I will consider a criteria that is given here, u less than or equal to f of y upon cg of y. If this criteria is met, I will accept the iteration and I will put x is equal to y. Otherwise, I will return to step 1. Here, I have introduced one new term, that is c. What is this c? C is actually an upper bound on fx and gx that is given here. Let c be a constant such that fy by gy is less than or equal to c for all y. Now what is a guarantee? That the random variable simulated through this process or this algorithm will give me a density f. So that question we will put it as a theorem, that is the random variable x generated by rejection method has density function f. Okay. So now if you look at this algorithm carefully, if I want to prove this theorem, what I need to understand is you look at the step 2. Given that u is less than or equal to f of y upon c times g of y, you are setting x is equal to y. Otherwise, you are returning. So, if I want to compute probability of x less than or equal to x, then that is equivalent to saying probability of x less than or equal to x is equal to, definitely y should be less than or equal to x, otherwise that is not accepted. Y should be less than or equal to x. At the same time, the iteration should be accepted. So step 2, that if condition should be valid, right? Only when this if condition is valid, then we are accepting this. So essentially, it is a conditional probability when y is less than or equal to x, given that u is less than or equal to fy upon cgy. Once we understand this, then the proof is very simple. So let us try to prove it again. So it is clear from the algorithm that this is satisfied, the first run. I'm just repeating the first line. So once this is satisfied, then what I need to do is I need to show that this particular x has a density which is f. So how will I show this? So since we are dealing with conditional probabilities, let us make them unconditional probabilities by doing this. So essentially what we have done here is it's like probability of a given b, we are writing probability of a intersection b upon probability of b. That upon probability of b is given by this variable k, this constant k. So essentially what we are doing saying is probability of x less than or equal to x is the CDF of y joint with u is less than or equal to this particular thing. So in order to compute this, we can actually compute while the CDF of y. We can actually use y and we can find out how it, so that can be done here in integral minus infinity to x. U is less than or equal to fy upon cgy. U is a uniform random variable. As you know, it will just replace capital Y with a small y. So fy by small cgy. Then what is the density of this particular thing? Y, that is g. So the integral over minus infinity to x, this accounting for u less than or equal to, this particular term is accounting for u less than or equal to fy by cgy, and this is the density of gy. This will give me this probability as usual upon k. Now you can see g of y will get cancelled, and what you will remain with fy by c integral over minus infinity to x dy. So that c is a constant, it doesn't depend on x, so it doesn't depend on y. So we can throw it out and it will give me 1 by kc in the denominator and integral over minus infinity to x fy dy. But what is f? F is nothing but the distribution which we want to simulate. Correct? So once we have this f, this will give me probability of x less than or equal to x. Right? Now the only way it can happen is this kc should be equal to 1. So can I get that? So in this particular case, you just see limit as extending to infinity. You will get this to be equal to 1. Therefore, k must be equal to 1 by c. Yes, that proves my theorem that the distribution generated by the algorithm that is given above is having density small f. This method has some significance which we will demonstrate through the following remarks. Example, this method was originally designed for random variables having support in the bounded interval. And in such cases, the distribution that was chosen, the distribution of y, was uniform AB. As we know, the uniform AB can be generated by using a simple linear transformation, that is y is equal to a plus b minus u. Therefore, we can simulate this random. This is a historic remark and it is credited to von Neumann. He is the first one to give this method. Now, he is the first one to give this method. Now, there are some other remarks which are somewhat technical remarks. In a sense, if we want to do something about these random variables, or can we do something better in these in this random variable generation procedure. So first, we have to see that we accept this value y with probability fy by cgy by generating u as a uniform random variable. So essentially what we are doing is we are accepting if u is less than or equal to fy by cgy, and that we have assigned a number which is 1 by c. Because the method, the probability with which this thing will be accepted, you just treat fy by gy as one number between 0 to c. It cannot be negative. So fy by gy is a number between 0 to c. Then probability of u less than or equal to fy by cgy will be 1 by c, because it's a uniform random variable. So essentially the number of iterations, so it is either a success or a failure. So we are having a Bernoulli trials with probability 1 by c. Correct? So the number of iterations required for this random variable will follow a geometric distribution with mean c. That should be clear, which is quite obvious from the method, the way the method works. Another technical remark which I want to emphasize on is this is the algorithm, and now in this algorithm, if you notice, we are generating two random variables at any given point in time. For example, y and u. Now the question is, can I save on one iteration? The answer lies here. Here, what we are doing is we are just using the value of u to either accept or reject. So actual value of u is not used. It's just that whether it is smaller or bigger is used. So suppose in some iteration, it so happens that u is greater than or equal to fy by cgy. Then according to this algorithm, it is a waste. You go back again simulate a random variable y and simulate a random number u. But with some finer observations, you can see that since you have already simulated y, so you have the realization of y. You have seen that after simulating a random variable u, you are leading to this zone, u less than or equal to fy. That means you will reject this. So now instead of throwing this random variable, use your iteration of y and get the value of fy by cgy and subtract it from u minus the constant, that is fy by cgy. Now if you look at this random variable, only the numerator fy by cgy, this random variable will be just translation of a uniform random variable from 0, 1 to some other constant interval of unit length. Correct? If I want to scale it back to uniform 0, 1, I will just divide this interval by the same constant and 1 minus the same constant. If you do that, what you are again doing is you are again generating a uniform random variable with 0, 1 without actually generating a uniform random variable. Now this generated random variable you can use to in your iteration to simulate the next criteria. So in the next iteration, you may have to simulate only y without simulating u. So that will save on some steps in the iteration. So that is what is written here. In the algorithm, we have never used the actual value of u. So using the next uniform, you may use this random variable u minus fy by cgy upon 1 minus fy by cgy as uniform random variable, and you will say one computational efforts of the random variable. Okay. Now let us try to demonstrate the applicability of this method for a beta random variable. So you have a beta random variable and you are trying to simulate something which is related to beta random variable. So in particular, you have a random variable which is beta 24. Fx is given by 20x into 1 minus x cube. Beta random variable has a support in 0 to 1. So it has a bounded support. Now I want to come up with an algorithm to generate a beta random variable. So if you look at the algorithm, what are the steps that you need? So let us go back to the algorithm. I need some y with density g, and I need to simulate a random number u. So now the question is, I want to choose some y with density g. So since it is between 0 and 1, the best random variable to choose is a uniform random variable. So I will choose uniform 0, 1 as my random variable, and gx is 1 for 0 less than x less than 1. And once chosen, I need to evaluate, if you go back to the algorithm, you need to evaluate a constant c such that fy by gy is less than or equal to c. This will be our next task. So I have chosen a uniform random variable. Now how to choose a constant c. So take the ratio fx by gx. Take the ratio fx by gx denoted by hx. Now these functions are very nice functions. So I can use my theory of calculus to simulate, not to simulate, to find the maximum value of this ratio. So set h dash of x is equal to 0, solve for x. So when I set h dash of x is equal to 0, I will get this. Now there will be two, as you can see, it is very obvious that 1 minus x square will be thrown out as common, and 1 minus x minus 3x will remain in the square bracket, which gives me 1 minus 4x, and therefore there will be two possible values of x, that are x is equal to 1 and x is equal to 1 by 4, of which x is equal to 1 is not a feasible value because I have already excluded that value by this condition. So the only feasible value is x is equal to 1 by 4. You can use a second order derivative test to check whether this value gives you a maximum or a minimum. But as you can see, it should give you a maximum from the shape of the function, and you can actually confirm that the second order derivative test will give you a negative number. Okay, so once we have assured that x is equal to 1 by 4 is the point of the maximum of this ratio, I need to find the constant c. So just substitute that point into the function. You will get some number. This number in this case is 135 by 64. You will denote it as c. 136. So you have figured out the random, the constant c. Now going for the algorithm, we need to have fx by cgx. So fx by cgx will be in this form: 256 upon 27 x 1 minus x cube. Okay, then we are ready to set algorithm. So what was the algorithm in the previous case? Let us go back and see. Simulate y with density g. We can simulate. We have chosen it to be uniform. Another random number u. So we are generating two uniform random numbers, and you will check whether u is less than or equal to this. We have figured out what it is, and we will simulate a random variable. We will get the random variable. So I have generated two random numbers, u1 and u2. u1 and u2 are generated. Then 256 by 27 u1 into 1 minus u1 cube is fx by cgx, and therefore you got this. And if it passes this test, then you will set x is equal to u1 and stop. Otherwise you go back to step 1. Now, how many times do I need to compute step 1? We have already seen that this will have some geometric progression. So in particular, the average number of times the step 1 will be performed is C is equal to 135 by 64. If you look at this number C, that means for every 2 point some steps generated, we are having a random variable generation. So it's only half of the times the random variable is generated when you are considering this particular algorithm. Okay. So now we will we will give one more example of this method. As this method is very popular, we will try to simulate a normal random variable using this method. So some tricky things are there. Suppose Z follows normal distribution with mean 0, 1. Then if you look at modulus of Z, then this modulus of Z will have a density function which is given by this. Why it should be there? Because Z follows normal 0, 1 means Z is symmetric about 0, and therefore you just put that density and close that density into a form where you are folding the density around 0 and overlapping it over the other. That gives you something like 2 by root 2 pi e raised to minus x square by 2. Once you have folded that density, you get this particular density. Now, once you have got this density, again, if I am using this particular exercise, that is rejection method, then I need to know what is a random variable that I will consider as a y. What is my y following g? So in this case, since I have something which is very similar to this particular term, that is exponential random variable. So I will choose my random variable to be exponential random variable. Okay. So, and to keep it simple, I will choose it to be exponential one random variable. Exponential, which means 1. So I know gx. Obviously, I need to compute fx by gx for 0 less than x less than infinity. Now, in this case, you don't have to rely on calculus methods. For example, you can easily see that fx by gx, if you take the ratio, will be less than or equal to root 2 e by pi, because if you just substitute it here as a ratio, then you will get this particular expression. Root 2 e by pi will come out as common, and you are getting this e raised to something which is always less than or equal to 1. So I immediately got that fx by gx is less than or equal to root 2 e by pi, which is a constant. Okay, then we are done. Then what we can, then if we use the algorithm that is given in the rejection approach, we will get a density of mod z, and we need to somewhat fine tune our procedure to get the density of z. We will see that in this algorithm. So first, our goal is to generate y with exponential 1, because my g is exponential 1, and as usual we will generate a random number u which is uniform 0, 1. fx by cgx is something that you need to compute, which is given here, right? Fx by cgx is given here, that is e raised to minus y minus 1 the whole square upon 2. But you observe this closely, this is equivalent to, if I take a log transformation, minus ln of u greater than or equal to y minus 1 square by 2, which implies x is equal to y, and you stop. Otherwise, you again go back and reiterate. Now it becomes more interesting, because you know if u is a uniform random variable, minus ln of u is an exponential random variable with mean 1. Now, considering this, what can you do? Can you improve upon the procedure? We will see that later. But right now, whatever we have got, that x is equal to y is the density for mod z. Now I want to choose a density for Z. So how will I do that? Now, if you look at the density carefully, we merged this density, we folded this density into one part. So essentially what we have exploited is the density is symmetric about 0. So if I want to open this, what I will do is I will assume that the simulation given to me, the simulated value that is given to me is positive or negative with probability half. We have already done this exercise when we generated a random variable, which is integer valued and coming from discrete uniform distribution when we simulated random permutations. So similar thing we will do. We will generate another random variable u, which is having uniform 0, 1 distribution. If this random variable gives a value which is less than or less than 0.5, then I will set the normal random variable to be equal to x. If this value is given to me is greater than 0.5 or greater than or equal to 0.5, I will set it to be minus x. So both positive and negative are equally likely. The distribution given by this particular procedure is naturally a normal distribution with mean 0 and variance 1. Now let us go back again with the observation that minus ln of u is an exponential 1 random variable. So can we do better here? So instead of simulating a random variable with uniform distribution, this is our previous algorithm. Instead of simulating a random variable with uniform distribution, you can as well simulate a random variable with exponential 1 distribution. Take same efforts, it's just log transform that you have to take. Once you have taken this log transform, the condition is very simple. The condition is y2 greater than or equal to y1 minus 1 square by 2, which is this condition transformed. And you go to step 1. Okay. And the third step remains the same because there is no change. With probability half, you will assign a positive value. With probability half, you will assign a negative value. Therefore, you have this particular setup. Now the question is, I know how to simulate normal 0, 1. Can I simulate a general normal random variable? Yes, the answer is yes, because normal has nice location and scale fixing. Therefore, if I have a general normal random variable w following normal mu and sigma square, then you don't have to simulate this random variable again. You can use this z and just multiply this z by sigma, add a factor of mu, you will get the iteration for random variable w. This is what you will do with rejection method for simulating normal random variable.